So in this video, we're just going to follow through with regards to defining the cell parameters more accurately so that we have a more accurate description of the cell with realistic IV parameters. So in the last video, we already made a kind of demo cell, so we're just going to load it here. And you might recall that the IV parameters are a little bit too optimistic for a multicrystalline solar cell. The VOC was somewhere in the neighborhood of 658 millivolts, as shown here. And moreover, recall that Griddler is using a network model of the solar cell, which means splitting up the cell plane into tens of thousands of nodes, each with its own voltage and diode characteristics. So in order to do quick work, we just simply define diode parameters related to the passivated area and under the metal contact. So there were really just two values that the diode J01 and J02 takes on, depending on whether we're talking about the region in between the fingers, which is passivated, or under the metal finger contact, or under busbar contact, which is under metal contact. So what we're going to do here is just be a bit more detailed and make use of the feature that Griddler actually enables you to define separate diode parameters depending on the location that you're at on the wafer. And this is called defining a spatial distribution of these diode parameters. Now you might have already noticed that besides each box that defines a certain parameter, there's also a little button that's labeled with this blue N. And in fact, this little button exists besides most of the boxes which defines the cell properties. If we click one of these, what we get is actually a page that allows us to define the spatial distribution of that particular parameter. On the right hand side is a picture of the spatial distribution of that parameter, in this case the front J01. So remember that front J01 was defined to be 200, and so the picture is just uniform 200 everywhere, right, as a start. If we enable non-uniformity, now it gives us a chance to define some non-uniform distribution. And we can do that one of two ways. The first way is just to use this inbuilt drawing tool. So just to give you an example, maybe we draw an X. X marks the spot. So in this X area, we have drawn another value, which is 400 femtoamps per centimeter square. So the yellow is 400 and the red, which is the background, remains at 200 per centimeter square. So we can just check out what that does. If we hit map at open circuit voltage, we map the diode voltage. So we see that the resultant voltage distribution at open circuit condition is now reflecting this non-uniform distribution of front J01. So in the X, the voltage drops to 653 millivolts, and elsewhere is more like in the range of 658, which was what it was. And the overall VOC has now dropped to 655 overall instead of 658. Now, of course, this is a kind of crude way to draw the distribution of front J01. It's not particularly accurate of a multicrystalline cell. So the more accurate way to define the spatial distribution is to import an actual image, either from a JPEG or a TIFF file. As you may know, there are many measurement tools that can deduce the spatial distribution of recombination parameters. So here I'm just gonna click import. And for our demo, of course, we have already something called J0.TIFF. It gives us this. So in this example, this J0 map is deduced by analyzing a combination of luminescence images and dark lock-in thermography images. And this is kindly provided to me by the German Max Planck Institute of Microstructure Physics. So after loading the pattern, what we still have to do is we need to normalize the picture. So that means we have to set an average value of this J0. And by the way, you see that now the number in the box next to J01 is now in blue. So blue indicates that this parameter now has a non-uniform spatial distribution. So again, now we can run the voltage map at open circuit condition, and we get something that far more looks like what one would see in a, let's say, a photoluminescence image, where the voltage contrast strongly follows the grains. The ability to define non-uniform distribution in a parameter is not only reserved for diode parameters like J01 and J02s, but we can do that as well for other types of parameters, such as the light-induced current density at one sun, or even up here, the parameters related to resistance. So coincidentally, I also have available a certain map of a kind of effective contact resistance, which is again analyzed by luminescence and dark lock-in thermography images by the Max Planck Institute. So I happen to know this distribution as well. So now if we simulate the voltage distribution with a certain current flowing through the cell, for example near MPP as shown, we also see now this pattern of uneven current flow because of a non-uniform distribution in effective contact resistance at the front grid. So in reality, although we have defined a non-uniform finger contact resistance at the front grid, the source of this series resistance may also be attributed to a non-uniform contact on the rear. But because the Max Planck Institute only had access to measurements which gives the diode voltage, so when they analyzed that, they ended up lumping both the contributions from the front and rear contacts to the front contact effectively. So now, if we run the IV curve of the whole thing, together with these non-uniform parameters, we might find something that's much closer to what one finds for a multicrystalline solar cell. So if we study the loss chart, now there is a very significant front contact resistance power loss component, because even the average value of the front contact resistance gone up from 2 to 13. So this video sums up how to import or draw yourself spatial distribution in cell parameters. That means Griddler is able to take advantage of spatial distributions obtained by measurement tools, either mapping tools like a 4-point probe, or a core scan, or an imaging tool like photoluminescence or electroluminescence. So it is really the computation engine that can assimilate all these kind of spatial data and then predict when all these data are inside the solar cell, how that would impact the cell efficiency.